Something was decided for you before you typed the first command on every Linux server you have ever deployed. In the moment before your SSH session connected and your terminal prompt appeared and the blank canvas of a freshly provisioned server presented itself as the starting point from which you would build the system whose purpose was the workload you had designed it to serve. Something that was decided not by you and not in response to any security assessment of your specific environment, your specific threat model, your specific network topology, or your specific data sensitivity requirements, but by the distribution maintainers whose defaults were chosen in the context of the competing pressures that default configuration design must balance between the security discipline that a server configured for the hostile environment of internet-connected infrastructure requires and the accessibility that a distribution whose installation experience alienates beginners through the friction of security configurations that require understanding before they can be successfully navigated loses the adoption, whose scale justifies the maintenance investment that keeping a distribution viable in the competitive landscape of Linux distributions requires, and whose resolution in favor of accessibility over security means that every Linux server you have ever deployed began its operational life with a configuration whose settings were chosen to make. The installation works smoothly and the initial experience feel welcoming rather than to make the server resist the categories of attack that the hostile internet, whose exposure your server's network connectivity creates, will subject it to from the moment its IP address first responds to a probe, whose source is one of the thousands of automated scanning systems, whose continuous operation against the entire addressable IPv4 space means that your freshly provisioned server with its default configuration, whose security implications you have not yet had the opportunity to address, was discovered, fingerprinted, and added to the target list of automated exploitation systems within minutes of its first network response, before you had finished reading the post-installation documentation whose security hardening section you were planning to get to after you had finished setting up the application whose deployment was the reason you provisioned the server in the first place, and whose urgency displaced the security hardening, whose deferral has left every Linux server you have ever deployed running with the dangerous default configuration that this examination will name, will demonstrate the exploitation of, and will show you how to fix, before someone who has already found your server through the automated scanning that found it, within minutes of its provisioning, finds the dangerous default configuration that the distribution installed and uses it to do what the dangerous default configuration makes possible. The dangerous default configuration that every Linux server you have ever deployed is running with is not one misconfiguration whose identification and remediation represents the complete security hardening of a Linux server that the title Singularity might suggest. It is the systematic pattern of default insecurity that spans the authentication architecture, the network exposure surface, the privilege escalation pathways, the service attack surface, the kernel security parameters, and the audit and monitoring visibility whose combined insecurity across every layer of the default configuration creates a server whose security posture at the moment of deployment is the security posture of a system designed for a trusted internal network operated by users who would never attempt to exploit the access they have, deployed instead, into the hostile internet-connected environment whose attack surface the default configuration was never designed to resist, and whose exploitation of the defaults is the systematic work of the automated tools, whose operation against the entire internet address space makes the discovery and exploitation of default configured Linux servers the efficient and scalable operation, whose results fill the incident response reports of the organizations whose servers were found, assessed, and compromised before the security hardening whose deferral made the compromise possible was ever implemented. The first dangerous default is the SSH configuration that every Linux distribution ships with, whose parameters were chosen for connectivity and compatibility rather than for resistance to the authentication attacks that SSH's internet exposure invites from the moment a server's port 22 first responds to a connection attempt. The default SSH configuration that your Linux servers are running accepts password authentication, which is the authentication mechanism whose vulnerability to brute force attacks, to credential stuffing attacks using the username and password combinations harvested from the data breaches whose aggregate has produced a credential database containing billions of tested combinations, and to the dictionary attacks whose automated execution against SSH port 22 represents the most relentlessly executed attack against Linux servers on the public internet, makes password authentication, the authentication mechanism whose presence on an internet-exposed SSH service is the presence of a door whose lock can be tried repeatedly without consequence until the combination whose success opens it is found. The default SSH configuration accepts connections from any source IP address without the source restriction that limits SSH access to the specific addresses from which legitimate administrative connections originate. The default SSH configuration permits root login, which is the configuration, whose elimination of the audit trail that privilege separation through user accounts and sudo provides means that an attacker who successfully authenticates to SSH as root achieves the complete system access. That root represents without the intermediate step, whose logging and monitoring the sudo privilege escalation pathway provides. The default SSH configuration uses the default port 20, which is the port whose universal association with SSH makes it the first port that automated SSH attack tools probe when scanning for SSH services. Concentrating the automated brute force and vulnerability exploitation activity against the port, whose SSH service, the default configuration, has made maximally accessible to the attack tools whose operation is calibrated to the default. The second dangerous default is the firewall configuration, which, on most Linux distributions at the moment of deployment, is the configuration of no firewall, meaning that every port on which any service is listening on the newly deployed server is accessible from any source address on the internet, without the network layer filtering, whose presence would restrict access to the services whose exposure the open firewall permits to the source, addresses and protocols whose access the server's function requires. The default no firewall configuration means that the database service whose installation you performed to support the application you were deploying, whose binding to local host you intended to configure before the server received production traffic, but whose configuration you deferred while completing the application setup, is accessible from the internet. At the moment, its installation completes because the firewall whose rules would have blocked external access to the database port is the firewall that the default configuration did not install, and whose installation you deferred alongside the other hardening steps, whose completion was planned for after the initial application deployment, whose urgency dominated the provisioning session. The scanning tools that probe the internet, address space for accessible database ports, finding the MySQL and PostgreSQL and MongoDB instances whose default installation bound them, to all interfaces without authentication configured because the default installation assumed a trusted environment whose absence the internet-connected deployment represents, exploit the no firewall default by accessing the database directly and reading, modifying, or deleting its contents without needing to compromise the application layer whose credential requirements the direct database access bypasses entirely. The third dangerous default is the service attack surface that Linux distributions create by installing and enabling services whose function supports use cases that the server you provisioned does not serve. Running those services in the background of the server's operation, consuming system resources, and exposing network ports and local attack surfaces whose exploitation provides the initial access or the privilege escalation that the attacker whose presence on the system in any capacity exploits to advance their compromise. The default installation of common Linux distributions includes services including the print spooler, whose CUPS implementation has been the subject of critical vulnerability disclosures, including the 2024 remote code execution vulnerability chain, whose severity was sufficient to generate the security community attention that vulnerabilities of its magnitude receive, the mail transfer agent, whose default installation and configuration exposes the SMTP port to the internet, and whose configuration complexity creates the misconfiguration opportunities whose exploitation allows mail relay abuse and information disclosure, the RPC services whose default installation creates the port mapper exposure that network scanning identifies and whose vulnerability history documents the exploitation categories that RPC exposure creates, and the various other services whose default installation serves the general purpose workload that the distribution was designed to support, rather than the specific workload that the server you provisioned exists to serve. Each representing an attack surface whose existence on your server is the existence of a vulnerability category whose exploitation you have not evaluated, because the service whose installation created the attack surface was installed by the distribution's default package selection rather than by your deliberate choice. The fourth dangerous default is the kernel security parameter configuration that the sysctl settings governing the Linux kernel's network stack, memory management, and security behaviors present in their default values at the moment of deployment, whose defaults were chosen for the broadest compatibility and the most permissive operation, rather than for the resistance to network-based attacks, the memory corruption exploit mitigations, and the kernel information disclosure prevention that the security-hardened sysctl configuration provides. The default kernel network parameters enable IP forwarding and configurations where the server is not functioning as a router and whose enablement creates the traffic forwarding capability that a compromised server's abuse for network attack facilitation requires. The default kernel parameters permit ICMP redirect acceptance, whose exploitation by an attacker with network access allows traffic routing manipulation. The default kernel parameters do not enable the SYN cookie protection, whose absence makes the server vulnerable to cyan flood denial of service attacks, whose execution requires only the ability to send TCP packets to the server's listening ports. The default kernel parameters do not restrict the kernel pointer exposure through the proc file system whose reading by unprivileged users provides the kernel address space layout information. The kernel exploitation techniques used to defeat the address space layout randomization, whose effectiveness depends on the address space information remaining secret from the attacker, whose exploit code requires knowledge of kernel addresses to succeed. The fifth dangerous default is the user and privilege configuration, whose insecurity at the moment of deployment creates the privilege. Escalation pathways, whose exploitation by an attacker who has gained any initial access to the system delivers the elevated privileges that the attack's objective requires. The default user configuration of Linux deployments frequently includes the existence of user accounts, whose presence the default installation created but whose necessity for the server's specific function has not been evaluated, whose password authentication remains enabled with default or empty credentials in some deployment configurations, and whose shell access provides the initial foothold from which privilege escalation proceeds. The default sudo configuration, whose permissiveness in some distributions and deployment automation tools grants the initial user account broad sudo access, without the command restriction that the principle of least privilege requires, represents the privilege escalation pathway, whose exploitation requires only the compromise of the initial user account, whose broad sudo access the default configuration provides. The default SUID binary set, whose presence on the freshly deployed server includes binaries whose SUID permission. The attacker's local privilege escalation toolkit identifies as the mechanism through which the privilege escalation from the initial user access to the root access that the SUID binary's execution with root privileges enables. The sixth dangerous default is the audit and logging configuration, whose insufficiency at the moment of deployment means that the attacker whose activity on the server begins at the moment of initial access proceeds without the audit trail whose creation would provide the forensic evidence that incident response requires to understand what the attacker did, what data they accessed, what credentials they harvested, what persistence mechanisms they installed, and what lateral movement they performed using the access that the server's default configuration made available. The default logging configuration captures a subset of the system events whose forensic significance justifies their capture, missing the authentication events whose logging identifies brute force attempts and successful unauthorized logins. The privilege escalation events whose logging identifies the sudo and SUID execution that privilege escalation uses. The file access events whose logging identifies the credential file reading and configuration file modification that post-compromise activity performs, and the network connection events whose logging identifies the command and control communication and the lateral movement traffic that the attacker's presence on the system generates. The security evidence establishing that these dangerous defaults are the real-world attack surface through which the Linux server compromises documented in the incident response literature occur rather than the theoretical vulnerability categories that security hardening guides address in the abstract comes from the sources whose authority on the subject derives from their direct observation of the attacks rather than from their theoretical analysis of the vulnerability categories. The Shodan search engine, whose continuous scanning of the internet address space indexes the services listening on internet-connected hosts, documents through its publicly searchable database the scale of the default configuration Linux server exposure whose existence the dangerous defaults whose presence on every freshly deployed server creates as the immediately discoverable attack surface. Searches of Shodan's database reveal the hundreds of thousands of internet-connected Linux servers whose SSH service is accessible on the default port 22 without source restriction, whose database services are accessible from the internet without authentication configured, and whose web server version disclosure through default server headers identifies the specific software versions whose known vulnerabilities the attacker's exploitation toolkit targets with the precision that version information enables. The Verizon Data Breach Investigations Report, whose annual documentation of the attack patterns responsible for confirmed data breaches represents the most comprehensive empirical study of real-world attack technique prevalence available to the security community, consistently documents the exploitation of default and misconfigured credentials, the exploitation of default-enabled services, and the exploitation of unpatched vulnerabilities in the default service installations as the attack techniques responsible for the server compromises that fill the breach report's Linux server incident category, establishing through the statistical analysis of actual breaches rather than through theoretical vulnerability assessment the real-world prevalence of The Shodan Trends data documenting the response time between a server's first Internet Visible Network response and its first appearance in automated scanning tool targeting lists establishes through empirical measurement that the window between deployment and first automated attack attempt is measured in minutes rather than hours or days, meaning that the hardening whose deferral while the application deployment is completed is a deferral whose duration in most real deployment scenarios extends beyond the window within which the default configuration's existence on the internet-connected server went undetected by the automated scanning infrastructure whose continuous operation ensures discovery within the discovery window that the minutes-level response time defines. The specific remediation sequence whose implementation tonight transforms every Linux server you're responsible for from the default configured attack surface that the distribution's installation created into the hardened system whose security posture reflects the hostile environment, whose exposure the server's internet connectivity creates requires moving through each dangerous default category with the specific commands and configuration changes, whose combined implementation addresses the systematic default insecurity across every layer that the dangerous defaults span. The first remediation is the SSH hardening, whose implementation begins with opening the SSH daemon configuration file by executing sudo nano etc config and making the following specific changes. Find the line containing password authentication and change its value to no, which disables password authentication and requires the public. Key authentication, whose cryptographic strength is not vulnerable to the brute force and credential stuffing attacks that password authentication invites. Before implementing this change, ensure that your public key has been added to the authorized keys file of the user account through which you connect, because disabling password authentication without first configuring public key authentication will lock you out of the server at the next connection attempt. Find the line containing permit root login and change its value to no, which prevents direct SSH authentication as root and requires the privilege escalation through sudo whose logging creates the audit trail that direct root login bypasses. Find the line containing port and change its value from 22 to a non-default port number above 1024, whose selection eliminates the server from the automated scanning tool, targeting lists that scan specifically for SSH on port 22. Find or add the line allow users, followed by the specific usernames, whose SSH access the server's administration requires, which implements the user-level access restriction that limits SSH authentication attempts to the accounts whose access is authorized. Find or add max auth tries 3 to limit the authentication attempts per connection to 3, which reduces the brute force efficiency by disconnecting after 3 failed attempts. Save the configuration file and restart the SSH daemon by executing sudo systemctl restart sshd, then verify the service restarted successfully before closing the current SSH session. The second remediation is the firewall configuration, whose implementation begins with installing the UFW firewall management tool if it is not present by executing sudo apt install UFW on Debian-based distributions, or sudo yum install firewall on Red Hat-based distributions. Configure the default deny policy for incoming connections by executing sudo UFW default deny incoming, followed by sudo UFW default allow outgoing, which establishes the default deny posture whose security is the security of permitting only the explicitly authorized inbound connections, rather than blocking only the explicitly identified prohibited connections. Add the specific allow rules for the services whose inbound access the server's function requires, including the SSH port, whose non-default port number you configured. In the previous remediation step, using sudo UFW, allow your chosen port DOST TCP, the HTTP and HTTPS ports. If the server hosts web services using sudo UFW, allow 80 Fautali TCP and sudo UFW allow 443i TCP, and the specific ports required by any other services whose external accessibility the server's function requires. Enable the firewall by executing sudo UFWs. Enable and verify the configured rules by executing sudo UFW status verbose, reviewing the output to confirm that the configured rules match the intended access policy, and that no unintended access is permitted by the configured rule set. The third remediation is the service attack surface reduction, whose implementation begins with the comprehensive enumeration of every service running on the server by executing sudo systemstl list units, type service, state running to identify all active services in sudo ss, tlnp to identify all listening network sockets and the services associated with them. Review the enumerated services and listening sockets against the list of services whose operation the server's specific function requires, identifying every service that is running but not required for the server's function. Disable each unnecessary service by executing sudo systemtl stop service name, followed by sudo systemtl disable service name to stop the service immediately and prevent its automatic restart at the next system boot. Pay specific attention to the print spooler service cups, the mail transfer agent postfix or sendmail, the RPC services RPC bind, and NFS common on servers not functioning as NFS servers, and the Avahi daemon Avahi, daemon on servers not requiring MDNS service discovery, each representing a service category whose unnecessary presence on internet-connected servers has been the subject of critical vulnerability disclosures, whose exploitation was possible only on systems where the vulnerable service was running. The fourth remediation is the kernel security parameter, hardening, whose implementation begins with opening the systl configuration file by executing sudo nano, etc. systl.d99 security.conf, and adding the following parameters, whose values implement the security hardening across the kernel's network stack and memory management behaviors. Add net.ipv4 forward and argrim0 to disable IP forwarding on servers not functioning as routers. Add net.ipv4.conf.all.send redirects or starger0 and net.ipv4.conf.default.send redirects or 0 to disable ICMP redirect sending. Add net.ipv4.conf.all.accept redirects for 0 and net.ipv6.conf.all.accept redirects 0 to disable ICMP redirect acceptance. Add net.ipv4.tcp sync cookies for 1 to enable CN cookie protection against CN flood attacks. Add kernel.randomize rva or space 2 to enable full address space layout randomization. Add kernel.tptr restrict 2 to restrict kernel pointer exposure through the proc file system to privileged users. Add net.dpv4.conf.dol.rp filter 1 to enable reverse path filtering, whose implementation prevents IP spoofing. Save the configuration file and apply the parameters immediately by executing sudo sysctl p etc. sysctl d99 security.conf. Then verify the application of each parameter by executing sudo systl parameter name for the parameters whose application the security hardening requires confirming. The fifth remediation is the user and privilege configuration hardening, whose implementation begins with the audit of existing user accounts by reviewing the etc. password file to identify accounts whose presence the server's administration does not require and whose shell access should be restricted or whose accounts should be disabled. Lock the accounts of users whose system access the server's function does not require by executing sudo usermod l s-sbin knowledge username for each identified unnecessary account. Review the sudo configuration by executing sudo vsudo and examining the sudo rules for the broad access grants whose replacement with command-specific access grants the principle of least privilege requires, replacing all grants with the specific command lists whose execution the user's administrative function requires. Audit the SUID and SGID binaries present on the server by executing find on perm 4000 o perm 2000 2 dev null and reviewing each identified binary against the list of SUID and SGID binaries whose elevated execution privilege the server's function requires, removing the SUID permission from binaries whose privilege is not required using sudo chmod us binary path. The sixth remediation is the audit and logging configuration, whose implementation begins with installing and configuring the audit daemon by executing sudo apt install audit on Debian-based distributions and enabling it with sudo systemctl enable audit and sudo systemctl start audit. Configure the audit rules, whose implementation captures the security-relevant system events by adding rules to the audit configuration using sudo audittil, including rules for authentication events using w var log doth.log, pwa k authentication, rules for privilege escalation using w ubsr bin sudo px k privilege escalation, rules for credential file access using w etc. passbis, p-r-way, kk identity, and w etc. shadow, p-bar-way, and k identity, and rules for SSH configuration changes using w etc. config, p-r-way, k config. Make the audit rules persistent across reboots by adding them to the exter audit rules.daudit.rules file. Additionally, configure the log rotation and retention settings for the audit log, whose size management the log rotate configuration governs. ensuring that the audit log, whose forensic value requires its retention for the investigation period, whose duration the incident response timeline determines, is retained for the minimum period, whose sufficiency for the retrospective analysis of security incidents the organization's incident response capability defines. What remains as a residual exposure after the complete implementation of all 6 remediation categories is the attack surface created by the application software whose deployment on the hardened server introduces the vulnerability categories that application layer security addresses independently of the operating system, hardening that the remediation actions implement. The zero-day vulnerabilities in the kernel and system software, whose exploitation does not depend on the misconfiguration that the hardening addresses, but on the vulnerability whose patch does not yet exist at the time of exploitation, the supply chain compromise whose insertion of malicious code into the trusted packages, whose installation the package manager performs without the verification that supply chain integrity checking provides, represents the attack pathway, whose sophistication exceeds the default configuration exploitation that the hardening addresses, and the social engineering and credential theft attacks whose success in obtaining legitimate administrative credentials bypasses the technical hardening whose resistance to technical attack the implementation provides. The honest assessment of why every Linux server you have ever deployed launched its operational life with the dangerous default configuration that this examination has described and remediated is the honest assessment that the defaults were not chosen maliciously, were not designed to create the attack surface whose exploitation fills the incident response reports, whose documentation of the Linux server compromises that resulted from default configuration exploitation establishes the real-world cost of the defaults whose insecurity the distribution maintainers accepted as the trade-off, whose other side was the accessibility that the secure defaults friction would have compromised. The dangerous default configuration is the configuration of a system designed to be installed successfully by a beginner and secured subsequently by an administrator, whose security knowledge was assumed to exist and whose implementation of the hardening was assumed to occur before the server's internet exposure made the default configuration's exploitation the automated scanning infrastructure's opportunity. Every server you have ever deployed began its life exposed. Everyone. The one running your application, the one hosting your database, the one serving your customers, the one holding the credentials that connect your infrastructure. Each one launched into the hostile internet with the SSH password authentication that brute force tools probe continuously, the open firewall that database scanners find within minutes, the unnecessary services whose vulnerabilities the exploit toolkit targets, the kernel parameters whose defaults the network attack tools exploit, the broad pseudo-grants that initial access converts to root access, and the absent audit logging that attacker activity proceeds through without the trail that detection requires. The automated scanners found your servers the day they were provisioned. They noted the defaults. They added the servers to the lists. And they have been probing the defaults ever since, waiting for the credential that brute force eventually finds, waiting for the service vulnerability that the next disclosure makes exploitable, waiting for the configuration mistake that patience and automated tooling eventually identifies. The remediation exists. The commands are not complex. The implementation of every remediation described in this examination requires less time than the recovery from the compromise, whose prevention the remediation provides. Open the SSH configuration tonight. Disable password authentication, configure the firewall, stop the unnecessary services, apply the kernel security parameters, audit the user privileges, enable the audit daemon. Because every Linux server you have ever deployed is running with the dangerous default configuration that the distribution installed and that the automated scanners cataloged and that the exploitation tools are probing right now in the intervals between the scans whose continuous execution against the entire internet address space ensures that the default configuration whose existence on your server has been known to the scanning infrastructure since the day of deployment will eventually be the default configuration whose exploitation delivers the access that patience and automation have been working toward since the server first responded to its first probe. The terminal is open on every server you manage. The commands are in this examination. The remediation takes tonight. The compromise, whose prevention it provides, takes everything. Choose tonight, open the terminal, fix the defaults. Before someone who found your server the day you deployed it finds the default that you have, not yet fixed, and does what the default makes possible while you're doing anything other than the remediation that you will wish you had done before they did. The default configuration is still running on every server. Right now, fix it. Starting with the first SSH configuration change, starting now.